Okay, so welcome everyone, and today we'll be talking about obviously the container storage interface working with the HP Ezmeral container platform. My name is Frédéric Passeron. With that being said, and no further ado, I leave the stage to you, Michael. Have a good session, and thanks for joining us today.
All right, excellent. Thanks, Fred. I'm happy to be here. My name is Michael Mattsson. I'm a tech marketing engineer at Hewlett Packard Enterprise. And what we're going to talk a little bit about today is how to use the container storage interface with the HP Ezmeral container platform. And you will be able to find me on Twitter, Reddit, GitHub, Docker Hub, Tumblr, and I usually have the handle Data Mattsson. And what I do at HP on a day-to-day basis is I do nothing but persistent storage, and I put together this workshop to kind of as a introduction and a primer on how to use all the CSI primitives, right? And I want to walk through a few PowerPoint slides here first before we kind of kick off. So we are going to talk a little bit about the Kubernetes fundamentals. We're going to talk about the container storage interface at length, and we're going to also be able to use the CSI primitives using the Jupyter Notebook Interactive Lab, right? So you will be given a workspace where you will be able to step through some of the scenarios like inspecting storage classes, creating persistent volume claims, attaching workloads, and all that good stuff, right? So I also used to have my SME with me here in the chat. I think he is on PTO. His name is Chris Snell. I can't see him in the chat here. So if there are any questions, some person from the HP staff should just interrupt me and see if there's anything we need to address.
We'll relay the question whenever. Don't worry.
Yeah, perfect, excellent. So what I want to do first here is kind of just give a crash course in Kubernetes. Kubernetes is a fairly new concept to a lot of people in IT, and we just want to set the record straight here. The different things that we're going to talk about today. We are on the same page on where in the space of Kubernetes we're actually going to manipulate workloads and so forth, right? And so Kubernetes is an open source container orchestration system for automating application deployment, scaling, and management. And that is a fairly good description that I've taken from the Wikipedia page, right? But it all kind of comes down to, all right, so that's cool, but what does it actually look like? So I have this Kubernetes crash course. It's a one slider on the architecture and where things run and so forth. And just imagine yourself being either a developer who deploys applications on Kubernetes, or you're an operator who manages the Kubernetes cluster, right? Somewhere you will be using the kubectl command and connect that to an API endpoint somewhere, right? And that is basically the API gateway to your Kubernetes cluster, to the management control plane, right? And normally you have an API server, you got your scheduler, controller manager, and so forth that store the state in the local database of a master node. Normally you would deploy this in an HA configuration where you would have a fully redundant control plane, and the data store that's distributed across the nodes is called etcd, right? And you run this usually in an uneven amount of nodes, like 3, 5, 7, etc., depending on the cluster size and the amount of API calls. You might need to scale that out even further, right? And if you're running like managed Kubernetes in the public cloud, you don't even see these nodes because that whole control plane aspect of it is managed by somebody else. On the other side of the screen here, we can see that we have a kubelet running on something called a compute node or a working node, or kind of depending on what background you have coming in here. But the most common term is you just call it a working node, right? And there you have the kubelet that are accepting API calls from the API server to schedule workloads on that particular node, right? And we all care about the containers themselves here, right? But in the world of Kubernetes, you have something called a grouping construct called a pod. And that pod will be any number of containers, right? So it's usually, sometimes it's just one, right? But you group them together depending on if there's like a microservices stack that you want to run in as a unit, you would have all those containers running within that pod. And then that's kind of where the consumer comes in, right? So basically your end user, like, so say that you're running a web shop on Kubernetes and your consumer is basically your customer, right? They come in through a different kind of access endpoint and they access the working nodes. They don't go through the master control plane. So they will be, their traffic will be sprinkled across the Kubernetes cluster depending on where that particular workload is running that is requesting. And in the most common case, you also have like an external load balancer that balances the traffic, both for the API control plane and for the consumer traffic, to make the access to the cluster fully redundant, right? So the API server can sprinkle API calls across the API servers here. The consumer side of the house will be able to, if you have multiple replicas of your web service running on each node here, the load balancer will actually be intelligent enough to understand where a healthy application is running. So the pieces that we're going to talk about today is kind of like, if we kind of inspect the pod here, we have in this case, we have a Redis database, we have a Postgres database, we have an Nginx web server, right? So that kind of comprises our application example here, right? And what is interesting here is that both Redis can be run as an ephemeral caching database, but it can also attach to an external volume to persist the key value store. And Postgres is very likely to require persistence, right? Postgres is a SQL, an open source SQL server, and it requires to be able to move the workload around or being able to restore the container. It needs to attach to the same storage for each time it starts, right? And that's kind of where we come in, where we want to be able to deploy a stateful application and attach that volume to that particular workload, right? And so that is essentially what the entire workshop is about. I'm going to pause there and see if there's any questions.
So unmute everyone. So if you have any question, well, that's the time. Feel free. And if you're too shy to speak, you can use the chat and type your question in, and I'll relay it to Michael if needed. If no, you can also use the reaction button, thumbs up if everything is on track. Well, okay, no questions, so that's fine. You can go on, Michael.
Perfect. So kind of honing in on the particular area we're going to talk about is the HPE CSI driver for Kubernetes. And this is kind of just like a bird's eye view of the architecture of the driver itself and kind of where CSI comes in. So CSI is basically a specification that allows a complete separation of concerns between the Kubernetes upstream project and the Kubernetes SIG storage community, where they provide certain components for Kubernetes to attach to external drivers, such as the HPE CSI driver. We have a CSI controller driver, we have a CSI node driver, and then we have a construct called a container storage provider. And that container storage provider is dependent on the backend, right? So we have a Nimble one, we have one combined one from Primera and 3PAR, and we also have other platforms in the works that will use the same construct, right? So that allows us to iterate really fast on new features and capabilities, both for the CSI driver and the container storage provider. And so, you know, going through, we are going to provision a lot of different resources on Kubernetes, right? So, but I just want to kind of get the very basic concept out the door here before we kind of jump into the workshop, right? So just imagine for a second here that we have a Kubernetes cluster running with the in-tree storage plugin. It might be running in the public cloud, or you might be running a CSI driver. The three basic API objects that are always available there is the construct of a storage class, a persistent volume claim, and a persistent volume. The storage class that is the cookie cutter template on how do I provision persistent storage on this cluster, right? So you have a provisioner, it's called provisioner example here, but usually there's like csi.hpe.com would be our provisioner. And then you have a set of parameters that are implementation specific. And once you have a storage class on the cluster, the user is then able to create something called a persistent volume claim, right? And where you will specify the access mode, read write once, read write many, or read only many, which depends on what kind of backend storage system there is. And you also specify how much capacity you want, right? And then it's up to the dynamic provisioner, the CSI provisioner in our case, to create a persistent volume. And that persistent volume then describes something we call an external volume, right? And that external volume will then be bound to the persistent volume claim. And at this phase, you will then be able to attach this persistent volume claim to your workload on Kubernetes. So you will, when you attach this persistent volume claim, you go into your pod that you deployed, you will see that you will have a 100 gig volume sitting on that particular mount point. So these are some of the basics. And we're also going to talk about volume snapshot classes and volume snapshots and a few other CSI specific construct during the workshop. So if there is no further questions, I will present to you the notebook server. So you should be able to go to https://notebooks.hpedev.io. You will be assigned a number from Fred, and or if you receive one by email, and the password is StuDisco2020. Let's see if there's anyone in the chat here. I need to exit my presentation here. Oh, it's not wrapped up just yet.
Everyone is able to access the URL. I pasted it in the chat, so just click on it and it should open up the very same window that Michael is presenting right now.
Oops, I've been restarted here. Let me.
Yeah.
Yeah, I logged in earlier today, and
yeah.
I don't know if I've been.
Well, there's a timeout. Yeah, don't worry.
So I just want to get this into focus and set the Zoom correctly here. Let me see. Yeah, so you can see this quite well, right?
Yeah, you can go F11 if you want to go full screen, or Control, or you're on Mac, so it's a.
Is that full screen? Can you see it now?
Yeah, wonderful, great. Yeah.
Perfect. Okay, so this is basically your Jupyter notebook workspace, and you should be able to, you should see this folder here, depending a little bit on where you are in the navigation, but in your home directory, there is a Discover folder, and you should also have a Workshop CSI folder. And here we have a set of workbooks, and what you need to go to first is the README First notebook, which contains all the kind of metadata about this workshop, right? So we're leveraging the HPE Ezmeral container platform. There's some basic descriptions on the lab flow. You can also, how you download this workbook to your laptop if you want to read it afterwards. And then I have the different labs kind of lined up here. And the only lab you need to do in order is to retrieve your kubeconfig file. The remaining labs you can do in any order you want. I am going to step through the labs in this particular order, and if there's time and will at the end, I will also do the optional lab 4, right? Because some of these are quite substantial, and some of them are a little bit easier. And kind of depending on questions and progress, we will do lab 4 if there's still time. So is everyone at the screen? Is there any questions? Anyone stuck? Does it work? All right, I'm going to assume we're safe to go here. So what you need to do is to click your kubeconfig file here, and here's also some basic tips for you on how Jupyter workbooks notebooks work. Right, is that you see this piece of code here with brackets in the left margin here. You can see it. I have a 1 there. That means the I think that's the exit code of that command when it ran last. You probably don't have any numbers there. And I can see that I already downloaded my kubeconfig. But at the end of the day, what you do here in these segments here is that you simply put your cursor in here, and you can hit the play button up here. So run the selected cell, and something will spin in the background, and you will get some output. And this is basically the terminal output that you would receive if you were running this command on this particular Linux host that we are hosting this workshop in. There's also another trick you can do, and that is like hit Shift and Enter. That will also execute the cell. And the next step is to head to Lab 1, Persistent Storage Basics. All right, here we go. So there's a lot of text in this workbook, notebook, excuse me, and it's kind of meant to be completely self-explanatory, even if you wouldn't have someone teaching this particular class, right? So, but what I'm going to do is I'm just going to glance over these things, and I'm just going to try to capture the concepts that we are exploring as we walk through the notebook, right? So one of the first things you want to do if you want to deploy a persistent workload on a Kubernetes cluster is kind of get an idea of, is there any storage classes available to me on this cluster? So that what you would accomplish with kubectl get storage classes. Oops, I was almost hitting the zoom button there. The formatting is not the ideal here, but what you will see here is that there are a bunch of different storage classes, right? And since this is the Ezmeral container platform, we have the Ezmeral data fabric, which is MapR provision as the default one, because that kind of comes with the cluster. We have a different storage class, and this is the storage class that we're going to use throughout this lab, which is called HPE Standard, and it uses the csi.hpe.com provisioner, right? And so the default storage class, basically, if you don't call out a storage class that you want to use when you create a persistent volume claim, that is the storage class that the PVC will map to, essentially. So we need to like call out HPE standard in all our provisioning workflows, and and everything is kind of pre-baked. You don't need to think about it, but that is something to have in mind if you're provisioning storage on a different cluster that has multiple storage classes. You can also expand information about the storage class by getting the object explicitly to a -o YAML, and this will kind of display the entire storage class, right? The specific parameters for the storage class is kind of the short ones here. The csi.storage.k8s.io, those are specific to the CSI sidecar containers, right? So the provisioner and the node stage, node publish, the controller publish, and the expander, they all need access to a certain secret that we've squirreled away in Kube system that the cluster can look up on how to connect to the backend storage system, which happens to be a Nimble array in this case. I also, throughout the notebooks here, put in like a set of links that are kind of good for like learning more like about the storage class parameters for the HPE CSI driver and the different platforms and so forth. And there's links like scattered around across the notebooks if you would like to learn more. The next set of exercises here is basically creating your first persistent volume claim. And the way this is laid out is that I have the persistent volume claim as YAML in the notebook, but all the files, all the YAML files are stored in the obj folder here, and where the raw YAML is stored, right? So you can download that as well. And if you want to. This notebook will actually be available on GitHub, the public GitHub, in a couple of weeks. So all these examples that I'm showing you here will be available. So what we want to specify here, since Nimble is a block backend, it requires read write once. We want to provision a 128 meg volume, and we want to specify the storage class name HPE standard. We also want to give it a name so you can reference it easily. All right, so we just hit play there. You will get an immediate response back from Kubernetes because the operation is carried out asynchronously, and you would also be able to do a kubectl get persistent volume claim, my first PVC -o YAML to kind of show you more information about your persistent volume claim. You will see here that the status of the claim is sort of like the most interesting one. You will see here that it's bound. You will have a read write once access mode on the claim, how large the claim is. But there's also a bunch of CSI specific parameters. Let me see, where are those? So you have the volume mode and the volume name, and that is basically like the backing PV will map to this name. And we also have the ability to provision something called block storage or volume mode block, and I'm going to walk through that example as well. All right, so we can see that we have our PVC, our volume is provisioned, and then we want to be able to attach the persistent volume claim to your workload. The workload we're going to be using here primarily is just a very simple tool called IOPing that will just inspect a mount point or a device inside a pod and perform a read IO of 4K on that particular piece of either it's a device or a path, right? So in this first one, I'm just going to read /data, and I'm going to mount my persistent volume claim on the /data mount point you can see here. So I'm just going to go ahead and deploy that. And it's essentially when you attach the volume for the first time, what happens is that the CSI driver will see, oh, this is a fresh volume that we haven't seen before. So it will format the volume with the file system that was specified in the storage class. We're using XFS by default, but you can use ext3 or 4 or Btrfs depending on what preference you have, right? But that will be created on the first attempt to mount the volume. You should then be able to do a kubectl get deployment, my first deployment. I'm also going to do a wide here to get more information on it. Yeah, so we can see here that we have the deployment is up. One pod is up to date and available, and it's responding. And the next cell here will essentially just show the logs from standard out from this deployment. And you should then be able to see something similar to this, right? We will see that, yeah, we issued a 4K IO and we read a 4K IO from /data. It's an XFS file system that is mounted from a multipath device that in turn then would correspond to the Nimble array that we have running for this cluster. So that's how simple that was. And the next set of steps here will illustrate a few other things that we can do with CSI. So we want to be able to resize a persistent volume claim, right? We want to be able to expand. There is no shrink, right? So you can only expand persistent volumes. So if I do the disk free inside the deployment, you will see here, yep, it's roughly 128 meg, 125 megs there. There's some metadata for the file system. And then what you can do is, you can also do a kubectl edit, but a kubectl edit requires you to sit in a shell because it calls the local editor to edit edit the YAML file. So what we want to do here, we just want to do a kubectl patch and supply the patch to that particular API object, right? So we will just say, yeah, I want to expand resources, request storage to 256 megs, right? And this takes a while to perform because the resizer wakes up every it's not a synchronous operation. So there's a thread that wakes up every so often and checks if there's any volumes that need to be resized. I can do a DF here now, and you will see it to still be at 128 megs. So I'm going to skip this and come back to this later and show you that the volume has actually been resized. Any questions so far? We're halfway down lab 1.
Again, speak up or use the chat as usual, but so far, no question.
All right, excellent. So
it's clear. That's the comment. So
yeah,
you're doing really good. Go
clear
ahead.
as mud. Clear as mud. Yeah.
No. I mean, the guy says it's clear, so I suppose he's.
All right.
That's all fine.
Okay. Perfect. So what we just did, we created a persistent volume claim that contains a file system, right? With CSI, you can also specify a raw block device, and the persistent volume claim that we're going to use to create this is this particular one here, where it says volume mode block. So the default volume mode is always file system. So if you specify block, you will then be presented with a block device inside your pod instead, right? Instead of the file system mount point. So I'm just going to go ahead and create that, and down here in our deployment, I've modified it slightly, right? So instead of having a volume mount and a mount path, now we have a volume device and a device path, but we're still referencing a persistent volume claim as we did with the file system. So we have a my block PVC that I just created, and we will then be able to see what the difference is here, because I also said that IO ping. Okay, so instead of pinging /data, I want you to ping /dev xVDA, which is basically a virtual disk device, right? So we deploy that there, and this comes up pretty fast, right? Because there's no file system creation or anything like that. So if the container image is available on the host, it will start instantaneously. You just have to rescan the iSCSI target here. So we should be able to log here. Yeah, we'll see here. Our logs here, we did a 4K read on the block device. We can actually see it. It is indeed a block device of 128 megs. And that's basically how you access a block device. There's also a question here if the IO is faster. And I don't think it is faster. When I was labbing around with this, there was slightly lower latency on the raw block device, but it's barely noticeable at this point. All right, so what we're going to do now is go back to see how the resize went. So we can see here, this is the output from the previous command, right? 125. And if we rerun this cell, we can see now that the block device have been expanded, rescanned, and also the host file system has been expanded as well, right? So that is all being taken care of by the node driver that sees, the device was expanded successfully on the back end. I'm going to go in and do an XFS resize of the file system. And here we go. We expanded our volume. All right, so there's a cleanup cell here as well. If you want to run that, it doesn't really matter because I'll clean up this environment afterwards, but this will basically delete all the API objects that we created, all the workloads and all the PVCs and all those things. There's also an introductory blog post here that introduces the CSI driver. If you want to learn more. So then lab 2, snapshots and clones coming up. And if there's any questions, please speak up. We just covered the basics.
No, but the student 302 managed to do the lab 1 without any issue. I mean, he's actually copied the result of the command with the resize of the volume, so showing 253 megs. So that's fine.
Oh, perfect. Excellent. All right, so the next exercise here is going to go through how to use snapshots and clones natively on top of Kubernetes using CSI. And this introduces a set of new API objects that we can inspect, right? So I've provisioned a volume snapshot class on the cluster, which is called HPE snapshot. And this also, the volume snapshot classes also allows you to have default ones, right? But since I didn't know who else is going to be a tenant on this cluster, we're going to call out the HPE snapshot class explicitly. And you can also learn more about this snapshot class by getting the full output -o YAML. You will see here, yep, we are referencing a snapshotter secret that is pointing to the Nimble array. So we should be able to use this with our existing storage class. And we're also adding our custom description on the snapshots, and that is completely optional. So what I want to do first here, I want to deploy a workload that we can manipulate and get the basically insert some data so we can snapshot that and see that my snapshotted data that I inserted actually will persist across accessing the different persistent volume claims that we will as we progress through the application lifecycle here. So what I'm going to deploy here in one go is basically one persistent volume claim of 320 megs. And the app that we're going to use as an example is a Redis deployment here. And we're going to do a persistent Redis by adding the append only flag to the deployment. And we're going to attach the persistent volume claim on /data. So we're going to do a kubectl create, and that will probably take a while here. But what we're going to do is once the deployment comes up here, we're going to basically use the Redis CLI inside the pod for simplicity here to set a new key, hp/dev. That's the folder and the key, and we're going to say this CSI workshop is awesome. You can actually change this string to something else if you want to see the actual results. So when you hit that, it will only return okay, right? It doesn't give you any more details than that. But what you can do in the next command here, in the next cell, is actually retrieve the key that you just inserted to make sure that it's actually in there, right? Yep. So this CSI is indeed awesome. And you would then, now we have this, so now the volume has a file system on it, it has a Redis store, and it also has this key, right? CSI workshop is awesome. So now we can create, when we create a snapshot of our PVC here, you see here, when we're referenced in the volume snapshot here, we specify the volume snapshot class name, which is HPE-snapshot, and we specify the source is going to be my persistent volume claim name that I just created, my Redis PVC. So you're going to go ahead and create that snapshot created, and then we can do a kubectl get on the particular snapshot. We will be able to see here, yep, it got created. It's called my snapshot. It's ready to use. It's their source PVC, restore size, and whatnot. And now you will be able to create basically a new persistent volume claim from this particular volume snapshot. And here, this kind of introduces a new stanza in the persistent volume claim, right? So you have here in the spec, you see data source here. You see that, okay, this data source, it has a name. It's my snapshot that I just created. You also specify what API kind it is, and it's volume snapshot. And since snapshots is actually a beta feature in the version of Kubernetes we're running here, we need to call out the API group as well. But that is something that will go away once the capability is GA'd. So you will only specify a name and kind in a future version. So we're going to go ahead and create that persistent volume claim. My clone PVC created. And next step, I'm going to create a new Redis deployment. I'm just going to call this my clone deploy. And the only difference here is that, yeah, all the metadata names are the same or different because we're going to run this in the same namespace. And the difference here is that the persistent volume claim, I'm going to point to my clone PVC, right? So I should be able to create this deployment. There we go. And once it comes up, you should be able to retrieve the key that you just inserted. Oh no, container not found. Yeah, so it hasn't been deployed yet. Container not found. Come on. There we go. So now we see that this CSI workshop is awesome. And that is the key that we inserted in our parent PVC. And that is now a restored PVC from a snapshot. So you would be able to, in the snapshot, you would essentially be able to overwrite that key or do any other destructive operation, and it would not affect the parent at all. So the next step here is to create a new persistent volume claim from another persistent volume claim. And this is basically creating a clone directly from the PVC itself without creating a snapshot in between. So what I'm going to do here, I'm just going to clean up a few things before we do that. It will delete the clone deployment because we're going to recreate it with a different PVC. And I want to also delete my snapshot and also going to delete my snapshot PVC. So there's basically no residual objects in the namespace after this operation completes. It's only the original PVC and the original Redis deployment. So when we create a new persistent volume claim from another one, which is basically, you use the same construct here in the spec data source. You specify name, my Redis PVC, and you specify the kind. You don't have to specify the API group because this is a GA capability to reference other claims. And you would then be able to derive that from the same storage class and all those things. And what happens here is that you won't create you will create a snapshot on the backend volume, but you won't be able to see this volume snapshot as an API object. As we go ahead and create that. Clone created. And now I'm just going to recreate the same deployment that I used for the previous PVC. And once that comes up, we should be able to retrieve the same key that we inserted in the original parent. Yeah, I don't know why Redis is taking so long to be stood up. Yeah, there we go. So now we created a persistent volume claim from an existing one, and that's how simple it is. So now you would be able, again, to do destructive operations on this or do some other transformation on the data. It wouldn't affect the parent PVC whatsoever. There's also a cleanup process here. I'm gonna run through that, hit play there. There we go. We also have a blog post that we wrote quite recently. I don't know, time flies when you're having fun. That kind of describes on how to use the CSI driver, snapshots and clones and volume expansion, because this was a capability that was kind of bundled together in a particular release of the CSI driver. So that kind of walks through a very similar scenario that we did here. But it uses Helm to deploy Redis instead of just using a single deployment. So any questions there before we proceed to lab 3, ephemeral inline volumes?
Seems not again. Everyone is on track.
Excellent. That includes myself.
No question. Okay, so you're fine, ready to go.
Perfect. So what we're going to do here is create something called ephemeral inline volumes. And this is a substitute for a different kind of storage construct that has been available in Kubernetes since inception. And that is called empty dir. So empty dir creates an empty directory on whatever node it's running on, right? And that is used for data that needs to be stored temporarily, that will only be available during the life cycle of the container or the pod, I should say. And once the pod disappears, get deleted or gets rescheduled, that data that was stored in that empty dir gets deleted. And it is a little bit impractical sometimes to use that construct if you're using very large data sets and you have certain performance characteristics that you want to limit. That empty dir is just like an empty directory on the host, shared with the host, and all the resources on the host is shared with other pods on that host, right? So the ephemeral inline volumes is essentially where you can declare an empty dir on an external storage system and use the external storage system to provision temporary storage to your pod. And the way this works is that you need to have direct access to the CSI driver to provision ephemeral volumes. And that means that you need to have like access to the CSI secret within the namespace you're deploying. So we have a separate array for these XSIs in the environment, right? So you will basically have full access to the backend, username, password, and everything to that array to be able to create the ephemeral inline volumes. And these fields here, the data fields in a secret, they are just encoded with base 64, right? So if you want to read one of these values here, like the service port 8080, you can totally do that. You would be able to read the password and all those things as well, right? So the secrets are basically just encoded. They're not encrypted. There are ways to encrypt data on Kubernetes, don't get me wrong, but that is not what a normal secret that's normally it's not the practice, right? So you protect data or sensitive fields in Kubernetes by using role-based access control and such, right? But in this case, since you need access to the secret, it needs to be available in your namespace. So to the workload here, what I'm going to do is I'm going to deploy a 3 replica version of a logger, and this logger is going to, what does it do here? It's going to write out my data, write out the dates to a text file. And the interesting piece here is that you have your volume mount here that points to a name, volume name, and a mount path to /data. So this file is obviously going to be written there. And then you see the construct here is basically you have a CSI stanza, specify the driver. So where's my secret? And you have the file system type that you want. And then you can specify the volume attributes here. And these are the 3 mandatory ones where you specify, I want an ephemeral volume, I want to use iSCSI, and you also specify the size of that particular ephemeral volume, right? There we go, we're going to execute that. So let's wait for it to come up here. There we go. So now we have 3 replicas of this particular instance running, or this pod running. And you can see that there's no PVCs. There's no persistent volume claims involved here, right? Because these are accessing the volumes directly. There's no intermediary, there's no storage class, there's no PVC involved, right? And you can also, if you look at the, you can also see that I'm almost nearly pressing the Zoom stop share button each time. You will see here when you hit the kubectl get pods -o wide and your application here, you will see that these are also running on 3 separate nodes, right? And it also illustrates the fact that each pod, each replica of your pod has its own ephemeral inline volume, right? Because these are read-write ones, ephemeral volumes, and each pod, each instance has its own temporary space. Let me see here what this does. It just shows you, yeah, so it basically grabs the first container in the replica set there and does a DF, and you will see that this is indeed a multipath device that's being served on /data. So there we go. We'll do a kubectl delete here on that deployment. It's deleted. There's a little summary here. We also have a blog post on this topic as well, on how to use raw block that we talked about in the first lab, and ephemeral inline volumes on Kubernetes, and describes a little bit like the real world use cases for these different constructs. So how are we doing on time here? I haven't looked at the clock for...
15 minutes to go, but you can go beyond or if needed.
Yeah, okay, gotcha. So we can do the optional labs here. So these are like all the things that I've shown up to now is basically CSI capabilities that are available to any CSI driver that have these different features, right? So it's not Nimble specific, it's not MapR specific, it's not Primera specific, right? But what I want to show in the next set of labs here, in the optional labs, is to show some of the non-portable features that we kind of differentiate our platforms with, right? So let's just look at the storage class here one more time. I'm going to show you something that is called a allow overrides. So we see here that the allow overrides parameters, we are allowed to override NFS resources, performance policy, limit IOPS, and so forth, right? And what do you mean override? How do I actually override that? And that is something that you can do as a user in your namespace, right? So you see here, you have the annotations metadata field here. You specify csi.hpe.com/limits throughput to 5. And that means that you will basically provision a volume that has this 5 megs per second limitation on the backend storage, right? So you can't perform more IO than you're limiting it to, right? So let's. So what I want to do here is I'm going to run a job workload, and that is like a one-off. And this is going to just run the dd command and read the entire block device from start to finish and exit, right? And then what it does when it exits, it will basically print, dd will print on the command line how it performed during that block copy operation. So I'm going to create here in one swift stroke here, I'm going to create the PVC, this PVC up here that has been annotated, and then I'm going to fire off my batch job. So what if you had access to the Nimble array here, you would be able to log into the UI and see that, all right, so the throughput on the volume has been capped. And what else did I set on it? Yeah, so I set a custom description on the volume, and you will see that it says my batch job on it, right? And this takes as long as it takes to read my 30, how big was the volume? 32 megs for 5 megs per second. So it should actually be done now. So let me check the logs of my job here. And we will see here, yep, we definitely did a DD operation. We read the entire block device from start to finish. Took 6 seconds, and it read it by 5 megs per second. If you would run this unthrottled, it will be in the hundreds of megabytes per second, right? And this helps you to kind of like keep your Kubernetes tenants kind of constrained on how much IOs they're consuming. And there might be like disruptive workloads that are sequential batch-oriented workloads that you kind of want to tone down when they run, right, from a storage perspective. And this is basically the construct you would use to do just that. So I'm going to delete that there. The next cool thing I'm going to talk a little bit about is the access modes. And as you may know, that the access mode read-write once, that means that only one pod at any given time is allowed to access the persistent volume claim, right?
Michael?
Yep.
I have a question.
Yes, yes, please.
Is this sort of a limitation, I mean, you know, the bandwidth limitation, is it true for Primera and SimpliVity?
No, it's not. Yeah, I should have probably highlighted that as well, because these parameters are Nimble specific, right? So Primera have, or 3PAR, I'd say, have some QoS features, and they are like specific for the 3PAR plugin, so to speak, right? And I don't know if SimpliVity has have the QoS constructs that you can declare in the storage class. If they had that you would be able to do the same thing here. I don't think the SimpliVity's CSI driver is as sophisticated as ours, so I don't think you have that ability actually, because I think they're just using the vSphere CSI driver.
Okay, and you're saying 3PAR and not Primera, so you're making a distinction between the two arrays as well?
Yeah, so that is probably also a little bit. So the 3PAR, I know that 3PAR had the QoS feature in their flex volume driver, so that's kind of why I'm leaning on that. But I know that the QoS features are coming to Primera as well through the CSI interface. It's not been implemented yet, but it's definitely coming, right? So. And you can learn about all these options on our documentation site, right? It's called scodhpdev.io, and that here you have all the container storage providers that we support, right? So if you go to Nimble, you will be able to see the common parameters for provisioning and cloning, and this is kind of where you would grab these parameters that you want to be able to override and whatnot, right? And the same thing for 3PAR and Primera. And they don't support as many parameters just yet, right? Because their CSP is fairly new. So you can kind of like toggle compression, set the snap CPG, and specifying provisioning type and things like that.
Okay, thanks a lot, Michael.
All right, so back to access mode. So the read write once mode that we have by default on our block-based backends, Nimble, 3PAR, Primera, and so forth, only allows you to access one volume from one pod, right? And a lot of workloads that you deploy on Kubernetes, they require something called read-write-many, and that means you will have multiple pods on multiple hosts accessing the same file system, right? And a good example of a such file system is MapR, right? The Ezmeral Data Fabric, as that product has been rebranded, and MapR also allows like a very scalable workloads to run on hundreds of nodes accessing the same data. But for the block-based backends, what we basically have the ability to do is to spin up a NFS server on the Kubernetes cluster itself, right? And NFS allows multiple clients from multiple hosts accessing the file system. So we spin up an NFS server that is being backed by a single read-write-once volume, right? And that allows that multi-access, right? So I'm just going to create the NFS PVC here, and you can see here that what I also do here, I annotate my PVC here that, all right, I want to set NFS resources to true, and that means that this persistent volume claim will create an NFS server on the cluster for you, completely transparently. You don't have to do anything manually. And you also specify the access mode read-write-many, and that means that the Kubernetes will allow multiple workloads to request this persistent volume claim, right? So now I'm going to bring up a 5 replica deployment of my IOPing command, and this will essentially, all these different deployments will read that same file system that has been mounted on /data, and it's calling out the NFS PVC there. So let me see how it comes up here. You will immediately be able to see, yep, 5 replicas is on its way up. One is already started.
Michael, there's a question. Is the NFS server a dedicated container within Kubernetes?
Yes, it is.
Okay.
Yeah, so it's a dedicated, it's using the NFS Ganesha open source NFS server that is being used for other vendors have similar implementations, and there's also open source projects that it's called like the NFS server provisioner that uses this construct as well, right? So this is nothing that is like unique to us, but it's more of a capability. It's more of a checkbox thing that we can do this automatically for the end user, right? So now we can see that we have all these 5 replicas up and running. And so what I'm going to do here is just I'm going to get the pods and I'm going to basically grab the last log entry from each of those running replicas here. And what we can see here is that, yep, we're reading a 4K IO from /data. We can see that this is an NFS4 mount point, and this is basically the pod IP address of the NFS server running on the Kubernetes cluster, and this is the export on that particular NFS server, right? And this means that each persistent volume claim that you creates its own NFS server, and we can run up to 20 of these per node, right? And you will also see here there's a slight difference in latency here, and that depends on how close you are to the NFS server. So I would only guess that one of these are actually running on the same host as the NFS server, or basically two of them. You can see here that you have a 520 latency here on two of the pods, right? And that means that those two pods are basically co-located with the NFS server, because the other ones with 800 or 900 microseconds here, they are running on different hosts, so you have network latency in between those. And that's it. So I'm just going to delete that there, and it will delete the deployment. It will delete the persistent volume claim, and that when you delete that persistent volume claim, that will also delete the NFS server and the backing read-write once volume as well. Right? And we're on top of the hour here, I think. So, or the bottom of the hour, actually, yeah. So we started half. So there, we also have some blogs on this, the NFS server provision here that what just talked about. There's a blog on the HP dev community, and we also updated documentation on the portal that I just show you. We call it SCOD, the HP storage container orchestrated documentation. So, and then we have the conclusion here. We would like you to learn more, of course. We summarize what we learned here, but we want to make sure you fill out the survey. Also sign up to the HP Dev newsletter. And there's also a logout function up here when you go to file logout, and we would like you to do that as well to clean up the resources to make room for the next workshop. If there's not any questions, I'm going to hand over to Fred.
Thanks a lot. I hope you enjoyed the workshop. Please. Okay, great. Please take a second just to fill up the survey. I copy-pasted the link in the chat, so just click on it and fill it out. That'd be great. Thanks for attending the workshop, and thanks again, Michael, for taking the time to work with us on this. I mean,
no problem.
Okay, great. So you can reach out to us on the portal. So the blogs that Michael was talking about are all actually located on this first link on the hpdev.io. You can also contact Michael on Slack. I mean, there is a dedicated workspace for Nimble. Or you can join us reaching out to our newsletter or by mail or on Twitter. Or if you're within HP or a partner, we have a Yammer group that you can also connect to. So all this information are available on the slides. And if you don't have the slides, you can still take a picture of the QR code and you'll get all the link in there. With that being said, wishing you a very good end of the day, and stay safe as usual, and take care. See you soon and have a good day. Bye-bye.
Bye-bye. Take care.
Yeah.
Thank you, Matt.